So we're going to talk about the integral test here. And we're moving into the section about series and sequence where we're just determining lots of different ways or methods to use that will let us know if a series or sequence converges or diverges. So we're going to start our discussion in the integral test section talking about series and sequence that only have positive terms, right? Not negative. And we can say that a series would converge if its sequence of partial sums, if all of those partial sums, the sum of one term, two terms, three terms, four terms, etc., all of those sums are bounded, right? So the sequence of partial sums is bounded. So we'll begin talking about non-decreasing partial sums. And what we can do is we can say, well, suppose that this sum, n equals 1 to infinity of a sub n, as long as a sub n is positive, dealing with an infinite sum, right? So if each of those terms is positive, then each partial sum is going to be greater than or equal to its predecessor. And what I mean by that is the sum of one term is less than or equal to the sum of two terms, and then the sum of three terms would be greater than both of those. The sum of four terms would be greater than both of those. All the way up to some sum of n terms. And we could even say, well, the sum of n plus 1. So this can continue going on. And what we're talking about here is a non-decreasing, everything's constantly getting a little bit bigger, so it's always increasing, monotonic, which is a fancy way of saying continuous, sequence. So thinking about that in this way, we develop a corollary, which basically says a series, and a corollary just says, it's something that goes along with things that we already understand. So a series n equals 1 to infinity of a sub n. As long as it is of non-negative terms, so everything is positive that we're adding up, we know that it's going to converge if and only if and only if, we write the IFF as a shorthand for that, if and only if its partial sums are bounded from above. So if they have an upper bound. So my shorthand of this first 3 minutes of discussion here is basically that if you are adding a positive term consistently as you calculate your series, each following term is going to be slightly greater, or at least equal to its previous term. So it's not going to be getting smaller. So we'll do an example here. I'm actually going to skip to the next page. We're going to talk about harmonic series. Okay, so we're going to consider the harmonic series. And this is the sum, in this case, of n equals 1 to infinity of 1 over n. So a harmonic series is a type of divergent infinite series. And if we started to write out the sums, plugging in n equals 1, n equals 2, we'd end up with terms 1 plus 1/2 plus 1/3 plus 1/4, continuing along to a plus 1 over n, and then infinitely it continues going. So let's think about what this looks like. I'm going to write out more terms here to explain this to us. So let me write out, I'm going to write out to the 9th term. So I'm going to look at the sum of these terms, in a sense, in groups. So this first one here, if I summed one term, and we're going to leave the very, very first term out. So my second term, we're going to treat that as just 1, and that would equal 1/2. And if I looked at adding 1/3 plus 1/4, well, 1/3 plus 1/4 is 7/12, right? So we get 7/12 here, which is approximately 0.58 repeating 3. And what we want to notice is that 7/12 is greater than if I were to add 1/4 plus 1/4, which 7/12 is greater than 1/2, right? So now I'll look at the next 4 terms. And if I were to add those together, I get a big ugly fraction, 533 over 840, which is approximately 0.63. So that 0.63, that value is bigger than 1/2, right? So if we could say, well, that's bigger than adding 1/8 plus 1/8 plus 1/8 plus 1/8, which is greater than 4/8 or my 1/2. And if I continued this, say I added up the next 8 terms, that same logic here, that would be like saying that this sum is going to be greater than 8/16, or the sum is going to be greater than 1/2. So in general here, looking at these sums, the sum of 2 to the n terms, and when I say 2 to the n, we've got 2 to the 0, 1 term, 2 to the first, 2 terms, 2 squared, 4 terms, 2 cubed, 8 terms, which is what I've illustrated above. The following set is always going to be greater than its predecessor. So each set, the last set of 8 terms, or the set of 4 terms, or the set of 2 terms, or the set of the 1 term, they're always going to be bigger than the term that was before them, excluding that very first term. And so because we can show this, we can say that the sum is not bounded from above, which would mean it diverges. Because it keeps growing. So we are showing here that it's divergent. And the last thing we want to talk about then is the integral test, which is what we're building towards. And the integral test is related to this harmonic series we just discussed. So let's look at one more example before we determine or define what the integral test is. So in this example, the nth term is going to be 1 over n squared. So we're dealing with the sum n equals 1 to infinity of 1 over n squared. And what we want to know is, does the sum or series, does this series converge? So as we examine series, one of the first things we generally do is we start listing out the terms. So I've got 1 plus 1/4 plus 1/9. We can do this all day. All the way up to some 1 over n squared term, which we could continue adding because this is an infinite series. So to determine its convergence, let's compare this sum, let's compare to the integral. Because the integral is the sum of all those rectangular areas under a curve. So we'll write this as an improper integral from 1 to infinity of 1 over x squared dx. Okay? So if I started listing out all of the terms of the series, I would come over here and say, well, the sum of my n terms is 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared. Continuing on to 1 over n. So essentially what we're thinking about is it's like we're taking 1 over x squared and treating it like a function, and we're plugging in these terms sequentially. So if I think about it as a function, I can write 1 or f of 1 plus f of 2 plus f of 3 all the way up to a plus f of n term. And so this sum that I have here is going to be smaller than if I said, all right, well, let's have f of 1 plus that integral from 1 to n of 1 over x squared dx, right? Because this right here is essentially what we are doing there. So if I add this plus f of 1 in the beginning, now this is bigger than what I had before. So let's think about this here. I can make an even larger sum. I can evaluate f of 1. If I plug 1 into 1 over x squared, I get out 1. But this integral I have circled here in light blue, that's a nth partial sum. It's finite. It stops at some n value. But what I can do is I can make this statement. So because that's a finite integral, if I come in here and I replace that with the improper integral from 1 to infinity instead of 1 to n. Now, this is bigger than what I had previously written. Okay? So, and what we're trying to show is that it is bounded above, that there's an upper bound here. So if I go about calculating this improper integral, and we did this in a previous chapter, essentially the integral from 1 to infinity of x to the negative 2 dx, that is going to equal negative x to the negative 1 evaluated from infinity to 1, which is negative 1 over infinity minus negative 1 over 1. So negative 1 over infinity goes to 0, and I end up with 0 plus 1, which is just 1. So now I have 1 plus this improper integral is 1, which is equal to 2. And so what I have done is I have created an upper bound that has a finite value. And so in this situation, since, remember S sub n was what was on the left, I have now said S sub n, the nth partial sum of any series, is going to be less than 2. It's bounded above by 2, so therefore it converges.